Hey everyone, this is Dr. Mungli. So today in this particular video, I am going to explain you on gluconeogenesis. Today I am trying in this video I am trying a different approach using a blackboard instead of what I generally used to do with the whiteboard, and also I have used the different colors so that we can understand this process in a proper way. Now, the gluconeogenesis is a synthesis of glucose molecule from non-carbohydrate sources. Now, the precursors for gluconeogenesis are the substrates for gluconeogenesis, or it is lactate coming from anaerobic glycolysis. That's one of the substrate for gluconeogenesis. Or it can be alanine that can come from proteolysis, skeletal muscle proteolysis, or it can be propionyl CoA that can come from oxidation of odd number carbon fatty acids, and glycerol that can come from breakdown of triacyl glycerol from adipose tissue lipolysis. Now these are the precursors for gluconeogenesis. In my previous video, I have explained the timeline for gluconeogenesis, glycogen breakdown, and then ketolysis and all that. So you can refer to my video on the timeline for gluconeogenesis. So you can get that video by typing my name and also as energy sources during fasting and starvation. And also I am going to give a link here in this particular video on that. So the substrates for gluconeogenesis is alanine coming from skeletal muscle. And also note that gluconeogenesis process, it begins 2 to 3 hours after meals, but it steams up 12 hours in fasting condition, and then it goes to peak by 24 hours, and it remains at peak for another 1 week, 4 to 5 days and 1 week. After that it falls, but not really to the zero or baseline, but it just takes a constant phase from 1 to 2 weeks. Okay, now the alanine in the first week, the proteolysis is the major source of gluconeogenesis. Alanine is the one which is converted to glucose. Then we have seen lactate coming from anaerobic glycolysis, propionyl CoA coming from oxidation of odd number carbon fatty acids, and glycerol coming from triacyl glycerol breakdown. Let's see each of them how they can be converted to glucose. Let's start with alanine. Alanine is initially it is converted to pyruvate by alanine transaminase enzyme. Alanine transaminase, it converts alanine into pyruvate, and that's a reversible reaction. Now alanine is going into pyruvate formation. Once pyruvate is formed, now the pyruvate has to be converted into phosphoenolpyruvate so that can be reversed into glucose formation. So but the problem here is formation of phosphoenolpyruvate into glucose, or sorry, formation of pyruvate into phosphoenolpyruvate. We don't have an enzyme to do that. So in order to overcome this, because in glycolysis the pyruvate kinase enzyme which converts phosphoenolpyruvate into pyruvate, it's an irreversible reaction. Now we cannot simply use pyruvate kinase to do this job. So in order to overcome this, so we have a separate enzyme to take care of conversion of pyruvate into phosphoenolpyruvate. So what all that enzyme? So it is the pyruvate gets down into the mitochondria and it will be converted to oxaloacetate. Pyruvate is converted to oxaloacetate. This job is done by pyruvate carboxylase enzyme. Here is the pyruvate carboxylase enzyme. So the pyruvate carboxylase enzyme is going to convert pyruvate into oxaloacetate. It's a mitochondrial enzyme, and note that it's a carboxylase. It means it needs A, B and C. It needs ATP, biotin, carbon dioxide, and also it needs magnesium. Now once you get oxaloacetate, the oxaloacetate is converted to malate in the mitochondrial matrix. Sorry, I'll have to take out the other pathway here. Pyruvate is converted to oxaloacetate. I'm going to use this molecule here, pyruvate into oxaloacetate. That's going on in the mitochondrial matrix done by pyruvate carboxylase enzyme. Now the oxaloacetate in the mitochondrial matrix is converted to malate. This is done by malate dehydrogenase enzyme, which is a reversible enzyme, but now it is about conversion of oxaloacetate into malate. Now the malate moves out of mitochondria into the cytoplasm. This arrow shows malate is moving out of mitochondria into cytoplasm. In the cytoplasm, malate is converted to oxaloacetate by cytoplasmic malate dehydrogenase enzyme, reversible reaction, and in this process NAD gets into the reaction and NADH plus H plus is released. Now oxaloacetate in the cytoplasm is converted to phosphoenolpyruvate. This is an irreversible reaction, conversion of oxaloacetate into phosphoenolpyruvate done by phosphoenolpyruvate carboxykinase enzyme. Now during this reaction we are going to use one molecule of GTP is used and it will be released as GDP. GTP is used and GDP is released. So the GTP that is used in this particular reaction can come from the TCA cycle substrate level phosphorylation, that is succinate thiokinase reaction. Okay, once you get phosphoenolpyruvate, now the phosphoenolpyruvate do not get down into pyruvate formation during gluconeogenesis. It doesn't. Why? Because the enzyme pyruvate kinase here, enzyme name here in the conversion of phosphoenolpyruvate into pyruvate kinase enzyme is inhibited, means it will be phosphorylated. Pyruvate kinase is phosphorylated and that's an inactive enzyme. That is why phosphoenolpyruvate, it is not converted into pyruvate during gluconeogenesis. Now the fate of phosphoenolpyruvate is it undergoes multiple reactions here which are all reversible reactions in gluconeogenesis. Phosphoenolpyruvate is converted to 2-phosphoglycerate, 2-phosphoglycerate is converted to 3-phosphoglycerate, 3-phosphoglycerate is converted to 1,3-bisphosphoglycerate, that's a reversible reaction, and 1,3-bisphosphoglycerate is converted to glyceraldehyde 3-phosphate. 1,3-bisphosphoglycerate converted to glyceraldehyde 3-phosphate. That's how you get glyceraldehyde 3-phosphate there. Now once you get glyceraldehyde 3-phosphate, so this glyceraldehyde 3-phosphate can combine with dihydroxyacetone phosphate to make fructose 1,6-bisphosphate. So this is the combination now. Glyceraldehyde 3-phosphate is a 3-carbon compound. Dihydroxyacetone phosphate is again a 3-carbon compound. They both combine to make a 6-carbon fructose 1,6-bisphosphate. That's a reversible reaction done by aldolase B enzyme. Now if you ask me how come you got dihydroxyacetone phosphate, for that you need to consider either 2 molecules of alanine here. So when we began, so we began with 1 molecule of alanine converted to 1 molecule of pyruvate, oxaloacetate, malate, back into oxaloacetate, phosphoenolpyruvate, glyceraldehyde 3-phosphate. You got 1 glyceraldehyde 3-phosphate there. Dihydroxyacetone phosphate, how do you get? You can get dihydroxyacetone phosphate from glycerol, which I am going to explain soon, or if you begin with 2 molecules of alanine here, you get 2 molecules of pyruvate, 2 molecules of oxaloacetate, 2 malate come out into the cytoplasm, make 2 oxaloacetate, 2 phosphoenolpyruvate and 2 glyceraldehyde 3-phosphate. Out of these 2 glyceraldehyde 3-phosphate, one of the glyceraldehyde 3-phosphate can be converted to dihydroxyacetone phosphate by triose phosphate isomerase enzyme. This is how one of the glyceraldehyde 3-phosphate go into dihydroxyacetone phosphate, another glyceraldehyde 3-phosphate is just remaining there. So they both can be condensed to make fructose 1,6-bisphosphate. This is how you get fructose 1,6-bisphosphate. Once you get fructose 1,6-bisphosphate, so it can be taken into glucose 6-phosphate. Initially it will be taken into fructose 6-phosphate. Fructose 1,6-bisphosphate is converted to fructose 6-phosphate and that job is done by fructose 1,6-bisphosphatase. Fructose 1,6-bisphosphate is converted to fructose 6-phosphate initially, done by fructose 1,6-bisphosphatase, and that fructose 6-phosphate can be converted to glucose 6-phosphate. That's a reversible reaction there. So glucose 6-phosphate can be formed there. Once you get glucose 6-phosphate, so the glucose 6-phosphate can be converted to glucose by glucose 6-phosphatase enzyme. So that's a gluconeogenic enzyme there. So this is how from 2 alanine you can convert 1 glucose molecule. So the 2 alanine here, 2 pyruvate, 2 oxaloacetate, 2 malate, 2 oxaloacetate in cytoplasm, 2 phosphoenolpyruvate, all the way to 2 glyceroldehyde. One of the glyceroldehyde is converted to dihydroxyacetone phosphate, another glyceroldehyde. Say they both condense to make fructose 1,6-bisphosphate, and then fructose 6-phosphate, glucose 6-phosphate, and glucose. Okay, so this way, in order to convert 2 alanine into 1 glucose, you need important enzymes here, and that is alanine transaminase, you need pyruvate carboxylase, you need phosphoenolpyruvate carboxykinase, then you need fructose 1,6-bisphosphatase and glucose 6-phosphatase. These are the enzymes, important enzymes that are needed to take alanine into glucose. Now let's see what all the enzymes that you need to convert lactate into glucose, 2-lactate into glucose. So that lactate is converted to pyruvate. This is a reversible reaction. So done by lactate dehydrogenase enzyme. Once you get pyruvate, you know what happens to pyruvate now. So pyruvate is converted to oxaloacetate, then it is converted to malate. Malate moves out into the cytoplasm, converted back to oxaloacetate, phosphoenolpyruvate, glyceroldehyde 3-phosphate, dihydroxyacetone phosphate. They both combine to make fructose 1,6-bisphosphate, then glucose 6-phosphate and glucose. So important enzymes that are needed here is lactate dehydrogenase, pyruvate carboxylase, phosphoenolpyruvate carboxykinase, fructose 1,6-bisphosphatase, and glucose 6-phosphatase. This is how lactate coming from anaerobic glycolysis can be converted to glucose in the liver and to certain extent in kidney. Now let's see how alanine is converted, propionyl CoA coming from odd number carbon fatty acids converted to glucose. Now the propionyl CoA, initially it is converted to methylmalonyl CoA done by propionyl CoA carboxylase. Now the methylmalonyl CoA is converted to succinyl CoA done by methylmalonyl CoA mutase enzyme. This methylmalonyl CoA mutase enzyme is going to convert methylmalonyl CoA into succinyl CoA. Once you get succinyl CoA, that's a TCA cycle intermediate. Succinyl CoA is converted to succinate. Succinate is converted to fumarate. Fumarate is converted to malate. Once the malate is formed, malate moves out of mitochondria into the cytoplasm, and malate is converted to oxaloacetate, phosphoenolpyruvate, glyceroldehyde 3-phosphate, and dihydroxyacetone phosphate into fructose 1,6-bisphosphate, glucose 6-phosphate, and then glucose. So in order to make 1 glucose, you need 2 molecules of propionyl CoA, because we need dihydroxyacetone phosphate and glyceroldehyde 3-phosphate down here to make fructose 1,6-bisphosphate molecule. Okay, so this is how odd number carbon fatty acid oxidation giving rise to propionyl CoA will give you 1 glucose molecule. Now let's move on to see how exactly glycerol coming from triacyl glycerol breakdown will give you glucose molecule. So that during lipolysis, adipose tissue breakdown, triglycerides are broken down into 3 fatty acids and 1 glycerol molecule. Glycerol is coming to the liver, and in the liver, glycerol is converted to glycerol 3-phosphate molecule. This job is done by glycerol kinase enzyme. So during this process, ATP is used and it will be released as ADP. So it means there is a consumption of ATP there. Now once you get glycerol 3-phosphate, glycerol 3-phosphate is converted to dihydroxyacetone phosphate done by glycerol 3-phosphate dehydrogenase enzyme. During this process, NAD plus is needed and it will be converted to NADH molecule, NADH plus H plus molecule. So that's what happens by glycerol 3-phosphate dehydrogenase. So glycerol 3-phosphate converted to dihydroxyacetone phosphate, and once you get dihydroxyacetone phosphate, so you make glycerol DH3-phosphate. It means with two glycerol molecules, you make two glycerol 3-phosphate, two dihydroxyacetone phosphate. One of the dihydroxyacetone phosphate is converted to glycerol 3-phosphate, glycerol DH3-phosphate. They both combine to make fructose 1,6 bisphosphate, glucose 6-phosphate, and glucose. This is how glycerol can be converted to glucose molecule. So in our body, these things can go on depending on what is available there. It can be one alanine making one pyruvate, one oxaloacetate, one phosphoenolpyruvate, one glycerol DH3-phosphate. On the other side, one glycerol making one glycerol 3-phosphate, one dihydroxyacetone phosphate. Now the dihydroxyacetone phosphate from glycerol DH3-phosphate from alanine or lactate, they both can combine to make fructose 1,6 bisphosphate, then glucose 6-phosphate and glucose. So it all depends what is available there. So now moving on with what all the important enzymes that you need in converting glycerol into glucose. So we need glycerol kinase, glycerol 3-phosphate dehydrogenase, fructose 1,6 bisphosphatase, and glucose 6-phosphatase. So these are the important enzymes. Now let's move on to see the regulation of gluconeogenesis. Now the regulation of gluconeogenesis can be done at hormonal like at the gene level, that is induction and the repression process. It can be done at the enzyme levels by allosteric modulation. First let's move on to see the allosteric modulation, and then I will move into induction and repression process. So first allosteric modulator on gluconeogenic enzyme is acetyl-CoA molecule. So whenever person is in fasting condition going into starvation, as you all know, there is a lipolysis going on, fatty acids are brought to the liver, beta-oxidation going on, acetyl-CoA is available plenty in mitochondrial matrix. So the available acetyl-CoA here, excess levels of acetyl-CoA, so it is going to act as a positive modulator on pyruvate carboxylase enzyme. So here is the acetyl-CoA. So acetyl-CoA is acting as a positive modulator on pyruvate carboxylase and keep this enzyme active where pyruvate is converted to oxaloacetate. That's one of the positive allosteric modulator there. Now the main control on gluconeogenesis will be going on over here. That is fructose 1,6 bisphosphatase enzyme is the main controller of gluconeogenesis here, and the regulator of this enzyme is fructose 2,6 bisphosphatase enzyme. In fact, this is fructose 2,6 bisphosphate. I have written it as fructose 1,6 bisphosphate. Let me correct it as fructose 2,6 bisphosphate. Now the fructose 2,6 bisphosphate, which is the main controller of gluconeogenesis process. So how exactly that happens? So as you all know, during fed condition, means when there is more insulin, there is high concentration of fructose 2,6 bisphosphate, and this fructose 2,6 bisphosphate on one side is going to keep PEPCK1, that is the rate limiting enzyme in glycolysis, PEPCK1, that is phosphofructokinase 1, active. At the same time, gluconeogenesis process is inhibited, or it will be negatively modulated by fructose 2,6 bisphosphate, having a negative effect on fructose 1,6 bisphosphatase enzyme. So it will be having a negative effect under fed condition. Now person is in fast, gluconeogenesis will be going during fasting and starvation. It means insulin is less, glucagon is more. So what glucagon does to fructose 2,6 bisphosphate is, glucagon is going to decrease the concentration of fructose 2,6 bisphosphate decreases during fasting condition. When the concentration of fructose 2,6 bisphosphate decreases, its positive effect on PEPCK1 is not there. It means glycolysis decreases, and also its negative effect on fructose 1,6 bisphosphatase is also not there now. It means now the fructose 1,6-bisphosphatase activity increases. That's what happens under fasting condition. So the activity of fructose 1,6-bisphosphatase is increased. Thereby fructose 1,6-bisphosphate is converted to fructose 6-phosphate. This is an allosteric modulator here on fructose 1,6-bisphosphatase. So under fasting condition there will be less concentration of fructose 2,6-bisphosphate. So thereby its negative effect on fructose 1,6-bisphosphatase is not there. That's why gluconeogenesis will go on in a faster rate. Now let's move on to see the genetic modulation, that is induction and repression process. Whenever a person is in fasting condition or stressful situation, so all the four important gluconeogenic enzymes, and they are the ones that we have already said, and that is pyruvate carboxylase enzyme, pyruvate carboxylase, phosphoenolpyruvate carboxykinase, fructose 1,6-bisphosphatase, and glucose 6-phosphatase. All these enzymes, so they will be induced by glucagon. So induction sign I have already given here as a green circle here. All these green circle basically indicates these are the enzymes that are induced under fasting and starvation. It means glucagon is going to induce pyruvate carboxylase enzyme, phosphoenolpyruvate carboxykinase, fructose 1,6-bisphosphatase, and glucose 6-phosphatase. Along with the glucagon, cortisol, epinephrine, and growth hormone. All these three hormones, they also induce all the four enzymes that I have mentioned in gluconeogenesis process. When the person gets into well-fed condition, when insulin is more, during that time pyruvate carboxylase, phosphoenolpyruvate carboxykinase, fructose 1,6-bisphosphatase, glucose 6-phosphatase enzymes will be repressed. So this is all about regulation of gluconeogenesis. So in this particular video I tried to explain the entire gluconeogenesis process, including all the precursors or the substrates for gluconeogenesis, and that is I have explained how alanine is converted to glucose, lactate is converted to glucose, how glycerol is converted to glucose, and how propionyl CoA is converted to glucose, and also the important enzymes that I have mentioned. So for each of these substrate molecule, and you need to remember all that because those are the things that can be asked in different types of exams. So we have pyruvate carboxylase, phosphoenolpyruvate carboxykinase, fructose 1,6-bisphosphatase, glucose 6-phosphatase on this side, and from glycerol side we have glycerol kinase, glycerol 3-phosphate dehydrogenase, fructose 1,6-bisphosphatase, glucose 6-phosphatase. From the propionyl CoA side we have propionyl CoA carboxylase, methylmalonyl CoA mutase, and then we have phosphoenolpyruvate carboxykinase, fructose 1,6-bisphosphatase, and glucose 6-phosphatase. That's all for gluconeogenesis. I hope this video helped you, and also the new method and style that I have used here. I hope you liked that. So if you like it, please comment below in the comments box, and also let me know your feedbacks. And if you like the video, kindly give thumbs up, and also for regular updates subscribe to my channel so that you'll get the notification in your email, so that you can watch the interesting videos, something which will be useful for your exam or to understand biochemistry concepts. Thank you all. See you next time.